All right, in this video, I want to begin a discussion on generalized linear models. And generalized linear models are defined by specifying two components. First is the exponential family distribution, which is for your response variable, or y. And then the second is the link function. Okay, so first right now, I want to focus on this first component here. And then we'll talk about the link function a little more later. So what is the exponential family distribution? So it looks like this. So we have our function for the distribution of y given theta and phi. This equals e to the power of, or the exponential of y times theta minus b of theta, so this is a function, b of theta, divided by a of phi plus c of y and phi. All right, and I know that at first glance, if you've never seen this before, you might be like, oh, what's going on here? Well, this is actually just like kind of a fancy way of generalizing a group of distribution functions that you're probably already familiar with. For example, you can show that like the normal distribution, the Poisson distribution, the gamma distribution, the binomial, the inverse Gaussian, they all can be written in this form. Okay, so for example, let me go ahead and show that the normal distribution is from the exponential family. All right, and then in doing this, we are going to identify what is theta, what is phi, what are these functions a, b, and c. Okay, so for the normal distribution. All right, so let's start with what is the normal distribution. For right now, I'm going to leave theta and phi, although the normal distribution, we write it with regards to mu and sigma, right? And so we'll have to identify what theta and phi are once we're trying to kind of get it into this format here. Okay, so the normal distribution is 1 over the square root of 2 pi sigma squared times e to the power of negative y minus mu squared divided by 2 sigma squared. Okay, so this is the normal distribution. So how do I make it look like this exponential family distribution? Okay, first thing I need to do is I need everything to be in the exponent of e, right? So what I can do here is I can say e to the power of log of the square root, oops, let me write this, 1 over the square root of 2 pi sigma squared. All right, and then you see these would cancel, and so I've done nothing to it, right? This is exactly the same thing. Okay, and then I'm going to leave this back piece alone for right this second. Okay, so I've done nothing here, right? But these guys cancel, and you could see that this is the same thing. All right, now log, or actually this 1 over square root, I can write this somewhat differently. Let me go ahead and erase that. I could write this as 2 pi sigma squared to the power of negative 1/2. That's the same thing, right? Okay, and now I can bring this power down. So let me go ahead and do that. Negative 1/2 log 2 pi sigma, okay? And then I have this other exponential here, so I can just use my property of, I have a product of two exponentials, and make that a plus sign. And then whatever I have in the back there. Okay. All right, so getting a little bit closer, now I have everything in the exponential, which the exponential family has to have that all up in there, all in the exponent, so that's good. Now let's go ahead and start kind of rewriting this. So I'm going to actually bring this piece up front, and I'm going to go ahead and square this out. So I have negative y squared plus 2y mu plus, or actually I guess that would have been a minus. Okay, minus 2y mu plus mu squared, right? So all I've done is I've squared this piece here, divided by 2 sigma squared. All right, and then I'm going to put this piece in the back. So I've just rearranged that sum. Did I drop a square? Yeah. Okay. Okay. So let's see here. I'm getting closer. I need y times theta. So let's look at what I have here. I have y times mu. So mu might be what theta is, right? And then phi, it looks like I have sigma on the denominator, or on the denominator here. So maybe sigma is phi. So let's start trying to rearrange this so that we have something like this. And then in the back, I need no theta, right? So no mu. So I have no mu back here. So it's looking pretty good. So just kind of rearranging things here. I'm going to go ahead and distribute that negative sign. And actually, let me go ahead and distribute this denominator to each piece for the time being. Okay, so this will be plus, so those two will cancel, and I'll have y mu divided by sigma squared. And then that'll be a minus. So I'll distribute that minus sign, and I'll have mu divided by 2 mu squared, or sigma squared. Okay, and then I not do anything to this back. Okay, so let's get it so that we have everything without mu in the back. Okay, so I'm just kind of rearranging once again. Now also I want on the denominator here, I want just sigma squared. So this piece here, I can write this as 1/2 mu squared. All right, so what I did is I took out this piece here, all right, and I wrote it like this. I'm going to move this in the back, minus, now I'm seeing I have negative on both of these, so let's go ahead and pull out the negative, and let's pull out the 1/2. All right, and I'm left with y squared over sigma squared, okay, plus this log of 2 pi sigma squared. All right. All right, now that I'm here, I'm starting to get really similar to what I see up here. So let's go ahead and formally, let's write that theta is going to be equal to mu, and phi is going to equal to sigma squared. And let's rewrite this. So I have y times theta minus 1/2 theta squared divided by phi, minus 1/2 y squared phi plus the log of 2 pi phi. All right, so now I've shown that this is the exponential distribution. This looks almost exactly like this. So let's go ahead and identify what A, B, and C are. Okay, so A of phi is just this denominator here, which is just phi. B of theta is going to be the second piece right here, this 1/2 theta squared. Okay, lastly, C of, usually we write y first, y and phi is this back piece back here, which is going to be this negative 1/2 y squared over phi plus log of 2 pi phi. Okay, and so knowing what these are and knowing how they're related to the exponential family is going to be really helpful later when I want to find, for example, the variance and mean for these exponential family distributions. So it is helpful to figure these guys out, and you can run a similar exercise, and it's fun to do so, and show that, like, for example, so we've shown that the normal distribution is the exponential family, but so is the Poisson, so is the binomial, so is gamma, and the inverse Gaussian. So this is kind of a fun exercise to run through on your own, and you can do very similar type of algebraic manipulation, really, to show that these distributions are also from the exponential family.